Okay, looking at some test problems. First equation, this one. You need to know the scheme for what you do to check to see if you have a method for solving the equation. This needs to be solved either as a separable or first order linear non-homogeneous equation, and those are techniques that you should know quite well. This equation is more resistant to being solved because it's not separable, and we go to the recourse because can't really, if we go through all the techniques we have, I don't think we're going to find one that's going to work for this equation. Okay? You've got to know the scheme for identifying equation types, knowing the techniques. In this case, as the instructions told you, go to a numerical solution. And the numerical solution is very straightforward. You're given that q of 0 equals 2. We start then on the q versus t graph at the point 0, 2. For this equation, we calculate the slope, which is your dq dt. Q is 2. So you got 1 minus 2 over 10. That gives you 0.8. The slope is 0.8. And since t equals 0 at this point, the t things don't make any difference. In this equation, for t equals 0, it gives you the same thing this one does. So for both equations, we get a slope of 0.8. Now I'm going to go ahead and draw a blue line segment here, right along with the green one. So we have a slope of 0.8. We use a step of 1 in the approximation. So if we move over 1 unit, we're going to have to move up 0.8 units since the slope is 0.8. And that gives us the 0.1. And we're at q equals 2. We're going to add the 0.8. We're going to get the 0.1 to 0.8 for both approximations. Now things start to change because the slope we get for the 0.1 to 0.8, well, we plug in 2.8 for q, we get a slope, dq dt is going to equal 7.72. So we're going to have a slope of 0.72, that's the green. And that's going to, when we move another unit in the t direction, it's going to get us out to t equals 2. We're going to be at the point 2 and the old coordinate 2.8. We add the 0.72 and we're here and we get to this point. For this function, we have t equals 1 and at this point t equals 1 and q equals 2.8. We put that in here and we find that the slope is 1.54.
Got the wrong one?
It's calculated somewhere down here. And that's an approximation. Could be off by 100th. Following that slope, starting at the point 1, 2.8, we end up at 4.34, if my arithmetic is correct. So we see that these two solutions begin to diverge. And if you then calculate the next step here and the next step here, you see this is going to end up concave down, this is going to end up concave up. Okay. Now, another problem, we have the equation y prime plus the square root of y equals 0. And I should have done y prime minus the square root of y equals 0, as you see in a minute, but this is something we can easily enough solve. We rearrange out to y prime equals negative y, and of course y prime is dy dt. This gives us dy over square root of y equals negative dt. Integrating both sides, we get this, giving us this solution. Then we say y of 0 equals 100, and we use that to calculate c. But of course, negative 1/2 t plus c quantity squared is going to be negative. It's never going to equal 100, so we have no solution for this condition. Now we had the equation y prime plus square root of y equals kt. That's not linear because you have a square root of y, so it's not, we can't treat it as a linear equation. It's not a Bernoulli equation, it doesn't fit the form of Bernoulli. It's not separable. We can check for exactness. This equation rearranged just to this, but the t derivative of your coefficient of dy is 0, where the y derivative of the coefficient of dt is not 0. It's not exact, so we're kind of out of bullets, and we don't really have a good way of solving this equation. So that's another one that would go to a numerical solution unless we can find some trick. Okay, and this is not what you need to see. This is. Okay. Okay, another equation was this one. Well, we rearranged this equation to the form of an exact equation, and we checked to see whether the x derivative of the coefficient of dy is equal to the y derivative of the coefficient of dx, in which case we would be able to, if we can do the integration, discover the function such that this left-hand side is a differential of that function, in which case the solution would be, well, that function equals some constant. Well, it doesn't work out. First of all, I distribute the 2 here, and then take the derivatives. The x derivative of this is equal to -1 over x to the 2/3. The y derivative of this is e to the y, and they're certainly not equal. So this equation is not exact, and you're not going to find another method to solve it because it's not separable, it's certainly not linear. So you're kind of out of luck on this equation. Okay, next situation was a logistic equation. Actually, this was next, but we'll do this one first. Where the limiting population is 100. Well, that means that your rate of change for logistic is a product of your population and your limiting value minus the population. And there's a constant in here, I'll just use k. So your dp dt would be this. Integrating this using partial fractions, we end up with 1 over L natural log of P minus 1 over L natural log of 1,000 minus P, absolute values of those quantities, equals KT plus C. And by what should be a familiar process, if you've done it several times, we've certainly done it in class several times, and people seem to be okay with it. We just go through this, and this procedure, this set of steps, and we get P over 1,000 minus P equals AE to the LKT, where A is not equal to 0. And we talked about why that is, but we've talked about it in detail before, so I'm just going to kind of invoke the steps here. And then we solve this for P. We're going to multiply both sides by this denominator, then distribute this through this, and bring all the P terms over onto the left side, factor out the P, and divide by the other factor. And we get our solution. And then we evaluate K by the given condition that the rate is 4, which means the derivative of our function over here, the function we get for P, would have value 4, meaning 4 population change of 4 per year, I think it was, or per month, or per unit of time. I forget what the unit of time was right now. When the population is 100. So you've got to plug P equals 100 in there and see where the derivative, take the derivative of your population function, plug in 100, and set that result equal to 4, you'll have K to solve for. Okay, up here, Bernoulli equation. I just ask you to do the change of variable, then I ask you to solve an equation that wasn't a Bernoulli equation because I had a wrong symbol in there. So this is all you'd be able to do, and I think at least one of the tests did a pretty good job of this. So the instruction was do the change of variable, to show the change of variable. Well, change of variable is V equals Y to the M, and you carry that out. So if V equals Y to the M, then Y equals V to the 1 over M. Take the derivative of Y to the M, keeping in mind that Y is a function of T, Now you're going to get my to the m minus 1 times the chain rule factor y prime dy dt. And then you solve this for y prime, because of course you have a y prime up here, and what you're trying to do is express this whole equation in terms of the v function. So y prime is this, very straightforward. Just rearranging this, you get y prime equals v prime over this stuff. I'm not going to read it to you, you can see it. Y to the m minus 1, we want this to be in terms of v, because we want to get all the y's out of our equation. So y is v to the 1 over m, we get v to the 1 over m to the m minus 1. That's in the denominator, giving us a v to the 1 minus m over m, times your v prime over m. And then we just plug that into the equation, and there is the change of variable. Now, as you know, we're going to do more with it. We're going to multiply by m, divide by the v to the 1 minus m over m, and all this is going to work out so that this equation becomes first order linear in v. This is going to turn out, if m here, arbitrary m here, turns out then to be 1 minus n. So if you choose to let m equal 1 minus n, you're going to get a linear first order equation in v, which you then solve, transform back to the y variable. And here we are once more with linear algebra, and we want our differential equations, and actually, yeah, that's all I see. I did one more thing, and see if I can find some board space to do it for you. Unfortunately, I washed that off. Up here, this will depict a barrel looking at side view in the water. Height of the variable, height of the barrel is here. Y is from the water surface, say, to the top of the barrel. You could also do from the water surface to the bottom of the barrel, it doesn't matter. You get net force on this thing equals the weight minus the buoyant force and we'll say that's W. Now the buoyant force I'm going to express as rho diff, and that stands for the difference of the densities. Density is often expressed by the symbol rho. It is the difference in the densities between the barrel and the water. So it's that multiplied by how much of the barrel's in the water. Well, how much of the barrel's in the water? That's H minus Y. Okay. Now this is kind of running together with this. Well, that's a net force. Well, the net force is mass times second derivative of your position function. So we have my double prime equals weight for all this. Okay, well that's nothing but a second order equation. You start by solving the homogeneous equation using the I'll write it up here, y equals e to the lambda t, or if you prefer a e to the lambda t. Actually, you've been using r, and we've been using r in this course. So it's a e to the rt. You get your characteristic equation for the homogeneous equation, you solve it, and then you worry about the non-homogeneous part. And you get a solution to the equation. And those are techniques that we went through well over a month ago. So that this is going to give you an oscillatory behavior. You push the barrel down, or if the barrel's below its equilibrium position, the position at which it would ordinarily float if interfered with. You push it down, it's going to come back up. It's going to come up by its momentum, it's going to come up higher than its equilibrium position. So it's going to fall back down. It's going to come up, it's going to come down. Now in the real world, that oscillation decays maybe exponentially. In the ideal world, we don't have any friction. It just keeps bobbing up and down in simple harmonic motion, which comes right out of the solution of the equation. So we want to understand this as kind of an intro to being able to understand the kind of oscillatory problem that I put on the test. Wasn't very good judgment. It maybe required a little bit more insight into the way these equations represent the real world. Okay. The equation itself is easy enough to solve. Understanding this connection is kind of the big deal.